Hi, I'm Charlotte, and I'm a fifth-year PhD student at Stanford, where I'm very lucky to be advised by Omer. And today I'm going to be talking about uncertainty quantification. And this is based on a long line of work that I've done while interning at Apple the past 2 summers, along with a bunch of great collaborators. And so broadly, the question of what we want from uncertainty quantification is when I have a question for a model. Let's say the question is, I've gotten an X-ray, I want to know, will my doctor prescribe a cast? Normally, the model can give me some prediction of how likely it thinks the doctor will say, yes, you need a cast. And uncertainty quantification asks that the model also be able to identify when it doesn't really know what the answer to this question is. So there's been a ton of work on this topic, but from a theoretical point of view, we want very strong guarantees about what exactly are we quantifying, and in particular, what actually are the underlying quantities we care about, and beyond this. So I think in practice, one of the main uses of uncertainty quantification is for error diagnosis. And so when I'm asking a model to say, I don't know, what I'm really asking is how much error am I going to suffer on this input? And this is useful for me as a patient, and it's also useful for practitioners to diagnose where is this model going to make errors and how could I improve it? And on this topic of how could I improve it, there's kind of a follow-up question, which is the uncertainty this model is experiencing reducible or irreducible? So you should think of irreducible as a case where, say, my X-ray is just blurry. And so no matter how many doctors I ask about this X-ray, they're not going to really be sure either. In the other case, the image is very clear, but the model just doesn't really know how to predict in this case. And this is a very important question in all sorts of decision-making contexts, as well as this error diagnosis context when we're thinking about how do we actually pinpoint model improvements. And so to start, I want to give a background on what actually calibration is, because it's this term you hear all the time in uncertainty quantification, and I want to talk about what sort of guarantees it gives and why we like it as a metric. And so going back to this example, I'm a patient, I go to a model, it gives me a prediction. A typical way we measure uncertainty is the predictive entropy. And so you should think of entropy as just a measure of how much randomness is in the prediction the model is giving me. And so in this case, the model is telling me, I can't really tell you better than a random coin flip what a doctor will say. So we think of this as having very high uncertainty or high entropy. And in an ideal scenario, I shouldn't just tell you the predictive entropy and stop there. I'd really like it to be connected to some underlying truth about the data I'm predicting. And so maybe I'd really like that the true label is quite random on these points where I predict 0.5. And this is exactly what calibration does. It gives us a way, given standard machine learning data, you can think of this as inputs, which is like the patient X-ray, we call this X. Prediction, so just think of a binary prediction, like I think this is 70% likelihood of needing a cast. And then ground truth labels, which we can think of as going to a random doctor and asking, does this patient need a cast or not? And calibration says, well, one way to check if our predictions really mean what we say is to look at aggregate statistics of our data. In particular, we're going to bin all of our data by our predictive value and look at what is actually the average true label in each of these bins. And so here I've taken a predictor that's predicting 2 values, and both, in fact, are calibrated, because in the bin where I predicted 0, in fact, all the doctors said no, there's no need for a cast in this case. And in the bin where I predicted 0.5, I actually did see a lot of randomness in what the doctors prescribed. So calibration is popular for good reason. We just saw how it really anchors a model's predictions in reality, what the ground truth labels look like, and it's also easy to check. So I just described the very easy way to bin your data and check that the empirical labels match what you're predicting. And just connecting it back to this entropy measure of uncertainty from before, calibration tells us that the predictive entropy really means something, in that when I give you the predictive entropy of a calibrated predictor, I'm actually telling you the entropy of the true labels in that bin. So in this talk, I promised I'm going to go beyond calibration. And so in the first part, I'm going to talk about a little more what calibration is giving us in terms of total uncertainty. And in particular, I'm going to connect it more concretely to the problem of error diagnosis and loss prediction. But in the second part of the talk, I want to think more about this decomposition between, does the model not know because the image is blurry, and if I asked many doctors, they would be in disagreement, or is the image very clear and my model is uncertain about whether all doctors would say yes or all doctors would say no? And we're going to see that calibration actually is insufficient to tell us which type of uncertainty we're experiencing, but we're going to look at an extension of calibration that does allow us to decompose our uncertainty estimates in this way. Okay, so starting with the first part of the talk, we're going to go back to this question of error diagnosis. And to make this problem concrete, I'm going to be thinking about a situation where my model gives a prediction P of x, and really my goal is to be close to the conditional true distribution of y given x, which will denote P star of x. This is the Bayes optimal predictor. And we measure how close our predictions are to this ground truth distribution by some sort of loss, which takes in either a label and a prediction, or we can express it in expectation over x as just taking in P star and P of x. And the problem of loss prediction is exactly this error diagnosis problem of when a new input comes in and I see my model's prediction, can I tell you and give an estimate of how much loss is my model actually going to incur on this point? And I want to dig a little deeper into how we think about losses because it's going to help us answer this question. And so let's take a look at the square loss, which is just the square difference between the true label and our prediction. The square loss has a pretty commonly used decomposition into two parts. The total loss is equal to what we can think of as the best possible loss we could incur if we actually knew the true conditional distribution, along with some additional loss that we incur because we don't do a good job of actually matching P star of x. And this is often known as the bias variance decomposition. And more generally, for many different losses we care about, we can recover this same sort of decomposition where the total loss can be decomposed into the best possible loss we would incur if we knew P star, along with some measure of how close are we to P of x. And so the important part is that this best possible loss has close relations to entropy functions. In particular, every proper loss has an associated entropy function that exactly captures this best possible loss if my ground truth distribution is P star. So for instance, in the case of cross entropy loss, this associated entropy would be the Shannon entropy. And so the takeaway here is that when I give you the predictive entropy of a particular prediction, it can be viewed as also estimating a loss. In particular, I'm saying, well, if the ground truth distribution is actually what I'm predicting, then this is the loss you would incur. And so this gives us a way to actually kind of build a loss predictor from just a prediction without any other machinery. In particular, given a point with a particular value, just predict its predictive entropy as the loss you will incur. And so we just saw a pretty clean example of if P is actually the Bayes optimal predictor, this would do pretty well. In particular, the loss we would incur would exactly just be the self-loss or the predictive entropy. And I should note that this idea of kind of treating P of x as the ground truth distribution has roots in all this work in outcome indistinguishability, where we're hoping to get a predictor whose outcomes are enough to let us estimate things about the true world. They look indistinguishable from outcomes actually sampled from P star. So taking this a little further, what if P isn't Bayes optimal? What can we say in this case? Well, I can give you an average guarantee, which is that if I condition on all points where P of x is a particular value, the bias of this estimate looks actually like a calibration condition. There's a little bit of this additional weighting function, h prime of v. You can forget that for now, but really the important thing is that I'm looking at the expectation of y minus v, condition on p of x equals v. And this is 0 exactly when p is calibrated. So this tells me that when I have a calibrated predictor, I get pretty good loss predictions on average over the bins where I predict a particular value. Yeah, so I think I want to note that this idea that the predictive entropy is a good estimate of the loss we incur over level sets is implicit in a long line of prior work on outcome indistinguishability, and it's in fact the tool we leverage to get things like omni-predictors or loss OI, for those familiar with that concept. And one thing to note is that this h prime of v essentially weights how much we care about the calibration of our predictor. If h prime of v is very small, then if our predictor is very miscalibrated, it's not as big a deal in terms of this loss prediction problem. And really what it turns out is what we need is this weaker notion of proper calibration, which has been explored in some of these works. So I told you how to use a predictor to get a loss predictor and how it has some guarantees when it's calibrated. But what's something that an alternative method that we could actually do? You could imagine doing a sort of meta-learning option where we just train an external model to predict our loss. So think of this as training a model that takes in an x, maybe information about the prediction, and then just predicts what loss we will incur. And this is a pretty common setup used in practice, especially for active learning. You'll often see a setup such as this, where we have a model, and then in parallel, a loss prediction module is getting trained. And as the model outputs predictions, the loss prediction model learns to predict the model's loss. And so these work pretty well in practice, but it, of course, requires a lot of extra time and samples and energy to actually train this separate loss prediction model, as well as keep it maintained as we update the base model. And so a natural question is, when do these complicated approaches actually do better than just using a model's built-in loss predictions? And our main takeaway here is that actually finding a good loss predictor has close ties to this problem of auditing for multi-calibration, which is a problem that a lot of people in this audience care a lot about and have done amazing work on. And I'm not going to formally define multi-calibration, but you should think of it as calibration was this guarantee that we wanted overall on all our data. Multi-calibration takes this a step further and says, conditioned on different demographic subgroups of our data, I still want to be calibrated. And so some intuition on where we get this result. Let's go back to this idea that miscalibration is related to a bad loss predictor. In particular, let's imagine we have a miscalibrated predictor where I'm predicting 0.1, but if I add up all the labels in this bucket, I'm actually, the average is 0.5. And so I can compute the true loss in expectation over this bucket as just the loss between 0.1 and 0.5. But my predictive entropy would be pretty far off from this estimate. In particular, I would think the loss is really, really low when in fact I'm suffering high loss. And an improved predictor doesn't actually have to understand what the loss is on a point-by-point basis, as long as it just understood that the average in this bucket is 0.5. And so it could do a lot better with just a single kind of constant prediction for all the points in this bucket. And so more generally, what we show is that if you can find me some loss predictor that's doing better than the model's self-entropy estimates, so I'm quantifying this in terms of square loss, so in a pointwise sense it's doing better, then I can actually find you a multi-calibration test function that is p of x is very miscalibrated on. So think about this as I've found you a group such that if you condition on this group, you're going to be miscalibrated. Yes. Yes.
Is the group the test function that you find?
Yeah.
Is it coming from a specific pre-specified class of test functions, or is it on? How is it?
That's a great question. Yeah, so typically we think of multi-calibration as with respect to this computationally bounded class. Here the test function we're going to get is going to depend on the actual loss predictor the superior loss predictor I've given you. And so if this is coming from some bounded class, then we can bound the sort of test functions we care about for multi-calibration.
Nice.
Yeah. And yeah, I've put this second arrow here with an asterisk to say that this is actually a two-way, mostly, relationship in that if you can find me a place where my predictor is really not multi-calibrated, then I actually have a way to construct a loss predictor that's going to do a lot better than the self-entropy estimates. And the reason I have an asterisk here is due to this kind of constant weight on the calibration error that we had from before. In particular, if I'm predicting 1/2, my self-entropy estimate says I'm going to incur a lot of loss, and it's kind of a self-fulfilling prophecy because you do end up incurring a lot of loss if you're predicting something with high uncertainty. And so in certain cases, I could have a very miscalibrated predictor, but the actual loss estimates are not that bad. Cool. So the takeaways of this section is that, well, if I give you a predictor and it's quite well multi-calibrated, you have good loss estimates. So multi-calibration is really the property that tells us when we could do good error diagnosis with just a predictor and not all this extra machinery. But going in the other direction, it also tells us that if I've found you a superior loss predictor that's doing really well, well, you could stop there and just use it for loss prediction, but it's also pointing out a place in which your predictor is actually wrong and giving you a direction to fix it by updating this miscalibration. And so really, maybe you should just use it to improve your model and get a better model. Cool, I guess I should ask, are there any questions about this portion of the talk before I move on?
I do have a question.
Yeah.
So proper losses are great, right? They actually recover the base optimal estimate. But most of the time, data is noisy, and the proper loss doesn't get you the noisy estimate that happens.
The noisy.
So P of y given x says your true posterior.
Yes.
But if your data was noisy, that wouldn't be the correct posterior for the noisy data that you're learning from. So proper losses really fail in that setting, but I don't know if that affects calibration in any way because you're basing it on that.
Yeah, I see that's an interesting question. We should maybe talk offline to make sure I fully understand, but I think that there's maybe a difference in how we're thinking about noise here, in that when my data is noisy and y given x is noisy, I'm thinking of this as actually the ground truth distribution. That y given x is noisy, and like the best thing I can do is predict the ground truth distribution, p star of x, and that will have pretty high loss. That's not something I can address without like actually digging into my learning task and figuring out how to, get more features or something like that. Does that?
There's a way to revert that. We'll talk about
Okay, cool. So, yeah, so far we've talked about calibration and multi-calibration and how this concretely relates to the problem of error diagnosis and how it gives us actual loss estimates for different points from our model. But now I want to talk a little bit about this decomposition. When is the model's uncertainty reducible? And by asking a doctor, I could get much lower loss, versus when is it actually irreducible and the doctors are in disagreement. So just to motivate why we actually care about this decomposition, a common situation that we often find ourselves in machine learning is that the model gives a prediction to this patient, and the patient could listen to this prediction, but actually they have a lot of outside options. In particular, the patient could decide to go ask a doctor, what do you actually think about this X-ray? Or they could decide maybe I should actually just go get more imaging and get some more information about my case. And sort of the naive approach to deciding when we should ask an expert would be one based on loss prediction, like we just saw. In particular, if my prediction seems like it's going to suffer high loss, maybe this is a case where I should ask an expert. But the key distinction here is that these experts are also subject to this inherent noise in our data distribution. In particular, even if this expert actually knew the best possible prediction, P star of x, it's not going to suffer zero loss. It's going to suffer this entropy of the P star, the irreducible loss. And so really when I'm making these decisions between should I ask an expert or should I trust my prediction, it's a question not of is there total high loss, but is there high reducible loss? So would my loss be greatly reduced by asking this expert? And so uncertainty approaches that allow us to understand how much of the loss is reducible and how much is irreducible would really help us make actually principled decisions in these sorts of scenarios. So let's make concrete a little more what I mean by reducible and irreducible. I kind of said at a high level that irreducible, often called aleatoric uncertainty, are situations when the image is blurry. This is formalized by the Bayes optimal prediction has high entropy. You can think of this as a situation where I asked many doctors and they're all in disagreement. The reducible case is one where the model is predicting 0.5 because it can't distinguish between P star of 0 and P star of 1. And in this case, you can think of it as, well, if I asked any doctor, they would definitely say yes or definitely say no, but I'm just not sure which of these situations I'm in. And the problem is that calibration really can't tell us which of these situations we're in. And why is this the case? Let's go back to exactly how we measure calibration. And so I've just visualized one of our calibration bins here. Think of this as all the patients that got a prediction of 0.5. And so this model is calibrated because, in fact, when we look at the true labels, half of the doctors said, yes, you need a cast. Half of the doctors said, no, you didn't. The problem is that beyond this, we could be in two very different situations. In what situation we're seeing half and half because asking a random doctor for each of these patients is roughly a coin flip with what they'll say. On the other hand, we could be seeing half and half because our bin is mixing up two very different types of patients. And so this uncertainty is really due to the model. And so in both cases, the optimal thing for our predictor to do was predict 0.5. It really didn't even have a language to start saying, I'm predicting 0.5 because the doctors are uncertain, or I'm predicting 0.5 because I'm uncertain. And so the key focus of this work is to ask, can we actually extend calibration to these uncertainty decompositions? And what I mean by extending calibration is that we want something that, like calibration, we should get uncertainty estimates that really ground this decomposition in what we're really seeing in the data. And it should be something that we can actually achieve and practically measure in certain situations. So as a first step, I kind of hinted in this calibration case that one of the main barriers to decomposing uncertainty is one of just the expressiveness of our predictor. In particular, a standard predictor just predicts a single value of the probability it thinks the ground truth label will be 1 or 0. And this single value really conflates these two types of uncertainty. And so we're going to need to move to what I'm going to call a higher order predictor, which rather than predicting what it thinks the value of the true label will be, you should think of this as predicting the value of P star. So this is a distribution over possible values of P star. And so this is, concretely, it's a mixture over probability distribution. And you've maybe never heard of a higher order predictor, but you've likely come across them in practice. Examples would be an ensemble model, where you have a large set of models which each give you some prediction, or any sort of Bayesian method that gives you a posterior distribution over possible predictions. And just to make concrete exactly what a higher order predictor is telling me, when I give you a mixture of particular points, what this is communicating is with half probability, I think all the doctors would say yes. But with some amount of probability, I think only 30% would say yes. And with the remaining probability, I think it would be half and half. And so we're really conveying uncertainty about the value of P star rather than about the value of the true label. Are there any questions about higher order predictors? Cool. Yeah.
So all of that is assuming that AI is not getting smarter than doctors, right? What if, that's kind of what we hope for.
I see. Yeah, I think, so like I've set up my learning task as the like ground truth is what would a doctor say. Right. And you're saying, well, what if there's an AI that has a better prediction? That's totally reasonable. I think you can imagine just switching out the learning task. In this case, we're trying to predict what a doctor would say. You could switch it out task. If I asked a very strong model, what would be the output of this model?
Right, but then there are kind of three levels, because for you it's like the model and the doctors.
Yeah.
And I'm thinking there's the model, the doctors, and the reality, which is even better than the doctors. And the AI can go through the doctors towards...
I see. Yeah, I think, so you're pointing out maybe an interesting question of like the limits of our data in terms of like, is there some true ground truth? And so I tried to set up this learning task where what the doctors say is really the ground truth, in that I'm asking, do I need a cast? Not like, for instance, is my arm broken? In which case, maybe the doctors could be noisy, but at the end of the day, my arm is broken or not. And so I think for all of these, you should think of situations where the labels I'm getting are the ground truth in some way, and the noise is because there is some inherent noisiness in what people would say. Think about like in language tasks asking like, is this a good summary of a book or not? You might have many different opinions on this, but there's not necessarily a ground truth on like, is this book good or not? I agree that you do run into a lot of situations where your data is kind of a proxy for some ground truth, and I think better understanding that is definitely an interesting...
I'm imagining maybe potentially an extension, because that's...
Yes.
There's one more level, so there's more, differences in...
Yeah, I think you would end up just needing some extra thinking about, like, to what degree is my data capturing this ground truth? What access to this ground truth do I have to kind of moderate the mistakes of my data? And I agree, it's very interesting.
One more. Yeah. I was just curious, like, since you've iterated the use of probability once, I guess it's always, can't help but ask if you can iterate it further. Like, not that you're going to do this in this talk, but is there a notion of, like, I could then have higher order predictors over higher order predictors where I say with probability 0.75 it's this higher order predictor and probably 0.25 it's some other higher order predictor? Like, is there a fixed point?
I mean, you can always iterate in the same way that, like, I can be uncertain about what my uncertainty is about my uncertainty about, so like you can go forever. I think the question is like, when does it cease being helpful? But yeah, you could certainly generalize this.
But there's some belief that one iteration is helpful, but more than that stops being useful or just stops being interpretable? Yeah,
I think that's a good question. I think one iteration is enough to answer these key questions that come up in practice about irreducible versus reducible uncertainty. I think further would give kind of confidence bounds on our estimate or something like this, which could be useful, but maybe aren't necessary to still get a practical implementation.
Great, thanks.
Any other questions? So step 2, now that we have this higher order predictor, how do we actually estimate what the uncertainty decomposition is? And we'll use something kind of analogous to how we used predictive entropy in the standard predictor case. So our total uncertainty, we still measure as just the entropy. And in this case, we're interpreting our actual prediction for a point as the mean of this mixture. So this is actually what we would end up predicting at the end of the day if someone said, okay, actually what probability do you want to assign to this point? And then we can further look at, instead of what is the entropy of the expectation of our mixture, what is the expectation over the entropy of the different components of our mixture? So, for instance, in the case where I'm mixing up p stars of 0 and 1, the total entropy would be very high. This is the entropy of a very random distribution. But my irreducible uncertainty would be very low, because the entropy of each individual p star is 0. It's either p star 0 or p star 1. And so irreducible uncertainty would be 0. Total uncertainty would be as high as possible. And we're going to define the reducible uncertainty as whatever we have left over. This is going to be non-negative, because usually entropy functions are concave, but basically it's just the gap that is left between our total uncertainty and our irreducible uncertainty. And so similar to calibration and predictive entropy, I've told you a way to give estimates of this uncertainty decomposition for a higher order predictor, but it doesn't necessarily have any connection to the real world data distribution. And for this, we're going to need a higher order notion of calibration. And first, I want to talk about what does it really mean to connect to the real world data distribution. I've just defined our estimates of irreducible uncertainty, which is the expectation of the entropy of the components. But for each particular point, there is some true irreducible uncertainty, which is a quantity we've been thinking a lot about throughout this talk. It's just the entropy of p star, the ground truth conditional distribution. And so ideally, this is what we want to be connecting to our estimates. When I give you a particular uncertainty estimate, it should be meaningfully tied to the entropy of this Bayes optimal predictor, at least maybe on average. And so this is exactly what higher order calibration requires. This should look a lot like first order calibration, but we've just taken a step up to higher order predictors. And so now my data looks like an input x, a higher order prediction, or a mixture, and then think of the ground truth as the actual p star value. I know that in practice, we don't get p star in our data. I'll tell you a little bit later how to relax this assumption. But for now, assume that we actually get access to p star. So what does higher order calibration do? It says, well, bucket by your higher order predictions. So I'm going to bucket all the predictions where I say half 0, half 1, and I'm going to bucket all the predictions where I say I think this is a pure mixture of 0.5. And what we're going to require is that the average mixture of the p stars in each of these buckets is actually close to the value we're predicting. And so going back to our example from before that calibration couldn't separate, we see that higher order calibration does give us a way to separate these two types of situations, because we're required to predict something very different in situations where we're mixing up zeros and 1 p star values versus in situations where the p star value is just a mixture of 0.5s. And so the theorem we can show, analogous to what we showed for first order calibration, is that, well, a higher order calibrated predictor maybe doesn't give you point-wise estimates of the true irreducible uncertainty, but its estimates are good on average over these level sets. And the proof is essentially one line from the definition of higher order calibration. Our irreducible uncertainty estimate is exactly just this expectation of the entropy of p stars, because we know the mixtures match, and thus it's the same as the expectation of this true irreducible uncertainty over our particular level set. And the interesting thing is we actually show that this is true in a bidirectional sense. So not only is higher order calibration sufficient to get these sorts of irreducible uncertainty estimates, but if I have a predictor that's giving me this property for a rich enough class of entropy functions, it actually necessitates that my predictor be higher order calibrated. I can't get away with some sort of easier notion. So I promised you that I would tell you a little bit about how to higher order calibrate when we don't have access to p star. And so I'll do that now. And so to think about how we actually higher order calibrate a predictor, you should keep in mind how we would calibrate a standard first-order predictor. In particular, we bin our data, and then we consider each particular bin. So think of this circle here as a bin data where I all have the same prediction 0.5. And so ordinary first-order calibration says, well, just look at the average label in these bins. If they match your prediction, you're good to go, no need to do anything. If they don't, update your prediction to match this true label. And so higher order calibration is very similar, but what we really want to learn is the true mixture of P star. And so we should partition into bins like this, learn the mixture, and make that our higher order prediction. And the key idea here is that this is really now just a mixture learning problem, which has been studied extensively in theoretical computer science, where we have some bag of biased coins, and we want to understand what is the distribution over biases of the coins in this bag. And the key insight from these areas of mixture learning is that it really depends on how we get to sample from our bag of biased coins. In particular, a typical way of sampling would be, let me draw a coin, flip it once, see if it's heads or tails, and then put it back in the bag, draw another one. And I can do this as much as I want, but at the end of the day, I'm fundamentally limited in how much I can learn about this bag of coins. In particular, I can learn the average bias of the bag. I see half heads, half tails. OK, the average is 0.5. But I have no idea if I've been drawing from a bag of fair coins or a bag of very, very biased coins. And this should really evoke these calibration issues that we were seeing earlier. And so the insights of this literature is that, well, let's start flipping the coin a few more times. How many flips do we need to start understanding properties of this bag of coins? And so to bring this back to our learning setting, where the takeaway is that information theoretically, if we're only seeing a single label for each point, we can't hope to do anything beyond what calibration was giving us. And so we fundamentally need to alter the sort of data we're getting. In particular, I'm going to assume we have access to what I'll call K snapshots, which is for a particular X, you see multiple Ys drawn from the true conditional distribution. And so in our patient example, you should think of this as asking multiple doctors, what do you think about this X-ray? Would you prescribe a cast or not? And I'll note that there are situations where we do not have access to K snapshots, but we've seen that this is really a fundamental barrier. So in these situations, we can't hope to do anything, but in situations when we do have access, here is where we can hope to say something about decomposing uncertainty. And I think any sort of situation where you have these sort of crowdsourced labels is one where we reasonably have access to K snapshots, as well as the problem of model distillation, where I'm trying to train a weak model based on some strong model who I treat as the ground truth. And so in such a situation, I can ask the model many times the same question to see what its distribution of answers are. Any questions about this? Yes?
Don't you have a high complexity in sort of how do you express P of X? Like if P of X is rather rich, it has many, instead of 4 different opinions, it has many, then don't you get like a pretty high complexity of your calibration?
You're asking how do you express the higher order predictor?
Yeah.
Yeah, that's a good question. I think there's a few ways to express it. I think for a K snapshot, so naturally, one way to express a higher order predictor, for the binary case at least, is a distribution over the interval 0, 1. And you're saying this is maybe a very complicated distribution. For K snapshots, you're seeing something a little more granular that you can discretize. So for 4 snapshots, for instance, you can think of this as I'm seeing one of 4 values. Either 0 doctors say yes, 1, 2, 3, or 4. And so you can have a little bit of efficiency in this way, but you're right that certain ways of representing a higher order predictor will come with a very complicated representation. Yeah. There's a question in the back here.
Thank you. I want to follow up on your hint that this sort of matches situation in which you have crowdsourced labeling tasks going on, which happen all the time, right? And I could see in the examples that I'm thinking of, we're working with the data set right now where hate speech was labeled, that of course there is a mixture depending on the background characteristics of those invoking on the labeling task. Similarly to what you said with the doctors and the X-ray, that some doctors might have had the experience that a cast is useful and others had the experience that it's not, and there isn't an absolute ground truth. It's still not entirely clear to me how you can, in these situations, distinguish, or what additional information you would need in order to distinguish the irreducible and the reducible uncertainty. Would it require for you to have information about background covariates that are relevant to this different perception of the situation, or how are you thinking about that if you were to do the next step to apply this?
Yeah, I think that's a great question that kind of echoes this question from before about kind of multiple tiers of ground truth. I think that, so in the setting where I am treating these crowdsourced answers as ground truth, I don't need this extra covariates. I'm truly treating the mixture of opinions as my ground truth distribution, and so the irreducible uncertainty is the best loss I could incur, or if I tried to predict what someone will say without any knowledge of like what are these background covariates. But I think it's a really interesting question to try to disentangle this further and understand, okay, there is a lot of entropy in these crowdsourced labels, but are there ways with access to more information to further understand, is this due to heterogeneous opinions, or is this truly just people of different opinions and you can't really predict? I think that kind of answers your question.
This also makes me wonder about the richness of representation, right? Because basically you live in a continuum, right? Like what feature set do I want? And the richer my feature set, the lower my Bayes error rate, but also the more complicated it becomes maybe because you have too many X's, yes, right? Yeah. If I have 10 X's I'll ever see, I can average over them. But if every X is unique, right, the only way to get to this is via repeated coin flips.
Exactly.
Yeah.
Yeah, no, I think that's totally true, that I think a lot of this abstraction depends on the fact that our features do not completely identify an individual. And thus when we say P star, there's a little bit of hand waving in that this is kind of averaging over the labels of the features we can identify. And yeah, this is totally true. I think I tried to point to this a little bit in this decision-making framework at the start, in that in some ways we can think of our features as this limiting factor. This is P star given the features we have, we can't go beyond this. But there are options like getting more imaging, adding a feature that can potentially further reduce the uncertainty that's present in P star. So yeah, super interesting question. So why do we care about K snapshots? Why are they helpful? Well, there's one pretty immediate reason why they're helpful, which is that, well, as K gets bigger and bigger, this is essentially a proxy for P star. If I ask enough doctors about a P star 0.1, I'm going to see that about 10% say, yes, you need a cast. And if I ask enough doctors about a 0.7, about 70% will say this. And so in general, this means that for large enough K, I can just treat these K snapshots as proxies for P star and approximately learn my mixture. So in many situations, if we do have access to a lot of snapshots, this is reasonable. But I think the slightly more interesting takeaway is that we can still do something with small K in certain situations. And this is really drawing on some of the work in this coin guessing literature, which says that, well, flipping a coin K times when I draw it from the bag gives me enough information to estimate the first K moments of the distribution of biases in my bag. And what this means for us is that what we really cared about in terms of our uncertainty decompositions were estimating this average entropy in the bag. And many entropy functions can be estimated from just a few moments. So as one example, the Brewer entropy, which is the entropy associated with square loss, this is a function of just the first 2 moments of the biases of the coins in the bag, which means that if we care about estimating uncertainty decompositions with respect to Brewer entropy, we just need to ask 2 doctors for each patient. So in this, from this point of view, it seems a lot more manageable than, ask as many doctors until you have a great estimate of P star. So to kind of make this a bit more concrete, we ran some experiments to see how do these higher order calibrated predictors actually perform in practice. And to do this, we used a data set where we do actually have access to some notion of irreducible uncertainty, and it's exactly in this crowdsourcing setting. So we took the classic CFAR10 image classification data set, which only usually has a single label per image, but some researchers out there took this data set and asked 50 human labelers per image, what do you think is in this image? And what you end up seeing is that there's a lot of variance in how much uncertainty there is in each image. And so certain images, the labelers see and they're like, yes, 100% very angry cat. But in other situations, we see a large distribution over what the humans label these images as. And so we're treating this as our ground truth P star in this case, and we'll compare our estimates of uncertainty to the irreducible uncertainty computed over the human distribution. And so what we see is that this graph is plotting the absolute error in terms of predicting the irreducible uncertainty as we increase our snapshot size. So kind of as promised by what I told you earlier, we do in fact see that the error is decreasing as we get more and more snapshots. But I think the interesting takeaway is that we're really getting diminishing returns after just a few snapshots. Yeah.
Maybe not so relevant here, but in the case of doctors, what if you ask for not 0, 1?
That's a great question. I think super interesting. And yeah, there's a lot of, I think there's this whole other direction of how do we elicit opinions from people. And people are a lot richer from 0, 1, but you do get this kind of noise versus precision in that if I'm saying like rate your, like give me actually your probability that you think this person needs a cast, people aren't very good at doing this. And so.
Right, but they might be able to tell you I'm certain or I'm not certain.
Exactly, yeah. So I think that's a super interesting question and yeah, raises a lot of other directions.
Kind of on a similar note and kind of going back to what you talked about with the teacher distillation, like what if you have a teacher model that are like Bayes models that's actually predicting not a giving you point-wise prediction, but giving you an actual distribution? Like, does that buy you more than a point-wise prediction, which is similar to what I think Jamie's asking?
That is a good question. I think again here we would be getting to this 2-tier thing of like the strong model is no longer the ground truth. There is some ground truth and it's communicating something about it. Yeah, it's a good question. I'm not sure what the right thing to do in that case would be. But yeah, we should talk about it. Nice. Yeah, so some takeaways of this section is we asked, how can we distinguish between reducible and irreducible uncertainty? And we saw that higher order calibration gives us a way to compute these decompositions that are meaningfully tied to the real world distribution. And we started with something that seemed a bit impossible that depended on P star, but then we saw that actually you can do this in an effective way with just access to K snapshots. And to wrap up, this was kind of the plan for the talk. I first told you about calibration, and we saw that calibration is very cleanly connected to estimating total uncertainty, and in particular, estimating the amount of error or loss we're going to incur at different regions of our model. But it fails to go beyond this and decompose uncertainty. And this is exactly what this higher order calibration work does. And moving forward, I think there's a few key open questions and directions I want to highlight. One that was maybe pointed to by Inbal is that there are some inefficiencies in how we're computing and defining higher order calibration right now. One noteworthy one is that it's inherently this partition-based or bin-based metric. I'm binning my data and then computing the empirical average. And this is kind of analogous to ECE in the standard calibration world, which many people in the audience have done a lot of interesting work on extending to notions like smooth calibration that don't suffer these binning issues. And so I think an interesting question is, are there relaxations of higher order calibration analogous to smooth calibration or other notions that give us more efficient estimates and better measurements of uncertainty decompositions without the need for this empirical binning approach? And then a last part that I think, again, has been alluded to a little bit in the questions from the audience is just extending these uncertainty questions to more real-world data complications. So one is this question of, what if these labels aren't actually giving me the true ground truth, and there's some kind of meta, secondary level of what is the actual ground truth? I think other questions are, calibration is inherently an in-distribution notion. Are there reasonable ways that are still somewhat rigorous to extend it to out-of-distribution data that we haven't seen before? And finally, what if we have weird correlations in our data? We were kind of assuming implicitly that each doctor is independent, but really, my doctor sees the X-ray and gives an opinion. The second doctor sees what my doctor said in the X-ray and gives an opinion. And so understanding what can we do in these sorts of situations, I think, is another really interesting question. So with that, I'll wrap up. Thanks so much for all the great questions.